Welcome to the deep dive. Today we're venturing into the online encyclopedia of integer sequences, the OEIS. For anyone studying number theory, you'll know the OEIS is, well, just invaluable. It's this huge catalog of number patterns.
It really is an amazing resource, a map, as you say, to patterns and connections, some quite unexpected.
Exactly. And today's sequence is OEIS A00026. The title is Even Sequences with Period 2n.
That title does pack a lot in.
It does. It mentions even sequences, a period 2n, and then connects it to even orbits of binary necklaces of length 2n under the group dnx_S2.
Okay, definitely a few terms there to clarify.
Yeah, let's break it down for everyone, especially our number theory students listening in. Maybe start with binary sequence.
Sure, a binary sequence is just, well, a sequence made up of zeros and ones, simple as that. Think computer code.
Got it. Zeros and ones. And period 2n.
That just means that the sequence repeats itself every 2n terms.
Right.
So the pattern restarts after that block of 2n digits.
Like a repeating wallpaper pattern, but with numbers.
Yeah.
Okay, now necklace, a binary necklace.
Right. Imagine taking that sequence of zeros and ones and arranging it in a circle, like beads on a necklace.
Ah, so the cyclic part is key.
Exactly. There's no fixed start or end. If you can rotate one arrangement to get another, they're considered the same necklace. Like 001 is the 010 wins the same as 100 if the length is 3.
Okay, that makes sense. Equivalence under rotation. Which leads us to orbits of a group action.
Intuitive. You have a set of things are necklaces, and you have a set of allowed transformations symmetries, like rotations.
Okay.
The group action is applying these symmetries. An orbit is basically a collection of all the necklaces you can reach from one starting necklace just by using the allowed symmetries.
So everything in one orbit is considered equivalent under those symmetries.
Precisely. We're grouping things that are fundamentally the same for the perspective of the symmetries.
And the specific group here is dn cross S2. Let's unpack those parts. dn.
dn is the dihedral group of degree n. It represents the symmetries of a regular n-sided polygon.
Like a triangle or a square.
Exactly. It includes rotations around the center end of them and also reflections or flips another end of them. So 2n symmetries in total for dn.
Rotations and flips. Okay, and S2.
S2 is much smaller. The symmetric group on two elements, it basically has just two operations.
Which are?
The identity do nothing and the swap. In our case, acting on binary necklaces, that swap operation corresponds to inverting the colors.
Changing all the zeros to ones and all the ones back to ds.
That's the one.
So dn cross S2 means we're considering combinations of these actions, like rotate and maybe invert, or reflect and don't invert.
Exactly right. A symmetry from dn paired with a symmetry from S2. Two necklaces are equivalent if you can get from one to the other using one of these combined actions.
Okay, that's a lot of potential equivalences. But then there's this word even. Even orbits. What's that about?
That tells us we're not counting all the possible orbits under dn cross S2. We're only counting a specific subset of them, the ones that satisfy some condition that makes them even.
And we don't immediately know what that condition is just from the title.
Not explicitly, no. But as often happens with the OEIS, the formula provided for the sequence gives us some big clues.
Right. So our mission for this deep dive is to understand what A00026 counts these specific even orbits and really get a feel for how group theory and combinatorics come together here.
It's a great example, actually. It shows how these abstract group structures help us solve very concrete counting problems, especially when symmetry is involved.
It feels like we're peeling back layers. Let's go back to the necklace idea. That length 3 example is helpful. 8 strings, but only 4 distinct necklaces under rotation.
Yes, 0, 0, they all do 1. 111, they all 1, 1. Then 0, 0, 1, which covers 0, 10, and 100 by rotation. And 0, 11, which covers a 101 and 110. 4 orbits under just rotation.
So that's the cyclic group C3 acting, but now we bring in dn cross S2, well, dn and S2 more generally, and for length 2n.
Correct. We have the rotational symmetry, potentially reflections too, depending on how we interpret dn acting on the 2, 2, 2 in positions, and crucially, this inversion symmetry from S2.
Flipping the zeros and ones.
Right.
So under dn cross S2, maybe 0, 0, and 111 become equivalent.
They could, yes. If the inversion operation is applied, 1,000 maps to 1 at 11. So they would likely belong to the same orbit under this larger group action. Same for, say, the 0, 0, 1, 0, 10, 100 orbit and the 0, 1, 1, 110 orbit. Inversion swaps those.
Ah, I see. So the inversion symmetry can merge orbits that were distinct under rotation alone.
It often does exactly that.
Okay, so we have the objects, binary necklaces of length 2n, and the symmetries, dn cross S2. How do we actually count the distinct orbits? You mentioned Burnside's lemma.
Yes, Burnside's lemma, sometimes called the Cauchy-Frobenius lemma or simply the orbit counting theorem. It's the powerhouse tool for this kind of problem.
And how does it work, essentially, without getting lost in the full proof?
The core idea is surprisingly elegant. It states that the number of distinct orbits is the average number of items that are left unchanged or fixed by each symmetry operation in the group.
Average number of fixed items.
Yeah. You look at each symmetry in your group one by one. For each symmetry, you count how many of your objects' necklaces, in our case, look exactly the same after you apply that symmetry.
Okay.
Then you sum up all those counts, one count for each symmetry, and finally you divide that total sum by the total number of symmetries in your group.
So sum the number of fixed items for every symmetry, then divide by the size of the group.
That's it. The formula looks like xg equals 1g times the sum of xg for all g and g.
Where xg is the number of orbits, g is the group size, which is 4n here, right? 2n for dn times 2 for s2.
Careful, the size of dn is 2n. So the size of dnx s2 is 2n2 equals 4n, yes.
Oh, right, 4n symmetries. And xg is the number of necklaces fixed by symmetry g, and x is the set of all 2m binary sequences.
Great.
Calculating that seems potentially very involved. You'd have to analyze all 4n symmetries.
It can be quite detailed, yes, especially figuring out the fixed points for combined rotation, reflection, and inversion symmetries. Yeah, but that's the process.
And the OEIS entry A00026, it basically gives us the result of that calculation, but specifically for the even orbits.
Exactly. Someone, likely Gilbert and Riordan, based on the OEIS references, went through the Burnside's lemma calculation for this specific group action, and then somehow filtered for or identified the orbits that meet this even criterion.
Okay, let's look at that formula on the OEIS page again. It depends on whether n is even or odd.
Right. For n even, it's an A0000000 when n plus 4 n2 1 2 and 2 and 2.
And for n odd, it's simpler. an A000000011.
Yeah. What's A0000011 again?
That's a more fundamental sequence. It counts the number of distinct binary necklaces of length k. Here k is 2n, or considering only rotational symmetry, it's derived using Burnside's lemma too, but just with the cyclic group SECO.
Ah, so the count for our more complex symmetry group, dnxs2, and the even condition is built directly from the counts under simple rotation. It seems so. The A0000019 term appears in both cases. This suggests the even orbits somehow relate strongly to the total number of rotationally distinct necklaces of length 2n.
And those extra terms, when n is even, the 4 to the power of something and 2 to the power of something.
Those likely come from analyzing the fixed points for specific types of symmetries, perhaps reflections or combinations involving inversion, whose structure depends critically on whether n, and thus 2n, has factors of 2.
So the parity of n really matters for how the inversion and the dn symmetries interact.
It appears to be crucial. The difference in the formulas is stark. It points towards the even condition being tied to how these symmetries behave differently depending on n's parity. Maybe it relates to whether an orbit is symmetric with respect to inversion or something along those lines.
Without diving into the original paper, it's hard to say for sure what even means, but the formula tells us how to count them, relating it back to simpler necklace counting.
Precisely. It's a common theme in combinatorics building solutions for complex problems, using results from simpler related problems.
It's really quite elegant, in a way. Now, you also mentioned connections to more advanced topics. Necklace posits.
Yes, that's stepping up another level of abstraction. You can define a partial order on the set of necklaces, often based on divisibility or embedding properties. This creates a structure called a posit, a partially ordered set.
Okay.
And there's a significant result that the posit of binary necklaces admits something called a symmetric chain decomposition, SCD.
Symmetric chain decomposition? Sounds complicated.
It is a rather advanced concept in algebraic combinatorics. But finding an SCD reveals a lot about the underlying structure and symmetry of the posit. It tells you the posit is highly organized.
Does that relate directly to the even condition?
Not directly in a way we can immediately see, probably, but it shows that these necklaces we're counting, even the even ones, are part of a much larger, beautifully structured mathematical landscape. It hints at deeper reasons for the patterns we observe.
Fascinating. So it's not just about the final number, but the structures these objects form.
Absolutely. The numbers in the sequence are often just the surface.
Okay, let's try to summarize what we figured out about A00026.
That's good.
It counts binary necklaces, so strings of zeros and ones in a circle of length 2n.
Right.
But not all of them. It considers equivalence under a combined set of symmetries, rotations and reflections from the dihedral group Dn, and inversion, swapping zeros and ones from S2.
Correct. The group Dn cross S2.
And even then, it doesn't count all the distinct orbits under Dn cross S2. It only counts the orbits that satisfy some specific even property.
Yes, that even filter is key.
The actual counting uses Burnside's lemma, and the final formula connects back, interestingly, to the simpler count of necklaces under just rotational symmetry, A0000001, with adjustments depending on whether n is even or odd.
You've got it. That captures the essence. It's a prime example of group actions in combinatorics.
It really highlights how powerful group theory is for tackling symmetry in counting problems.
Indeed. It provides a systematic framework.
And for students using the OEIS, it's a reminder that sequences can link together and sometimes hide deeper connections to areas like necklace posits. There's always more to explore.
Definitely. Following the references in the OEIS, like the Gilbert and Riordan paper mentioned for this sequence, is often the next step to really dig into the details, like that exact definition of even.
Exploring related sequences too, like A000000018 or A000000013 or A0000208, could show how these ideas evolve.
It often creates a web of related concepts.
So maybe a final thought for our listeners to ponder. What could that even property actually be? How does inversion combine with the dihedral symmetries to create this distinction?
That's the perfect question to leave hanging. It's about the interplay of symmetries. Thinking about which necklaces or orbits might have special properties under inversion could be a path forward.
A great puzzle. It just shows the world of integer sequences is full of these intricate mathematical stories waiting for a deep dive. Thanks for joining us on this exploration today.